I'd like to invite Liron David, a researcher from Tel Aviv University.
Okay, hi everyone. Thank you. I'm very delighted to be here. I'm going to talk about passwords, and I'm going to show you a system that can estimate the strength of a password using some learning process. But before I'm going to start, I have some question I would like to ask you. It's regarding passwords, of your choosing of your password. So when you need to choose your password and you are asked to have at least one capital letter. So how many of you choose the first letter of your password to capitalize this letter? Yeah, okay. Now, when you choose your password, you also required to have at least one symbol, which is one special character. Now, how many of you choose the exclamation mark as your special character and put it at the end of your password? Yeah, okay. And another question, how many of you use your personal information inside your password? Okay. Your name, your family name, your children, birthday, and so on. Okay. Okay. So I'm going to use it and I'm going to show you so that actually you're not the only person who's going to do that. Actually, most of the people do exactly what we've seen now. So we're talking about password. So of course it's important to have a strong password for all our profile, whether it's for our Facebook, bank account, eBay, LinkedIn, and so on. But the question is, what does it mean a strong password, right? We all want strong password, but what does it mean a strong password? So a strong password, like generally talking, is the one that cannot be easily cracked using brute force attack. So in order to achieve strong password, most of the website actually forces the user to have at least one capital letter, at least one lowercase, at least one digit symbol, and at least 10 characters in total. However, this policy does not necessarily guarantee you a strong password. And why? So let's assume we have the following password, which is New York 12, and then the exclamation mark. So as we've seen, and also you said, most of the people actually capitalize the first letter of your password, and then they add the 1, 2 at the end, and then they put the exclamation mark at the end. So the cracker, actually, they're well familiar with this behavior. So they can crack this password very, very fast, although this password actually meets all the requirements, which is capital letter, lowercase, digit, symbol, and 10 characters. So this is not a strong password, although it meets the requirements. Therefore, what we need is to have a better password strength estimator. And this is what we did. So this is where our algorithm comes in. So what we did is we developed an online password strength estimator, and by we mean me and Professor Avishai Wool. This is a joint work with Professor Avishai Wool, and this system called PES rank. And how does it work? So this system actually learns the common password people tend to do and the common transformation people tend to do, going over a huge corpus of leaked password that we can find on the internet. And then given a new password, our system can say how strong the password is. So how are we going to do that? So we consider 5 transformations most of the people tend to do. So first of all, they start with some base word. This is like the base password, let's say password. And then what most of the people do, they add some digits and some symbols before this base word, before this password. And we call this transformation the prefix transformation. Then what they do, they add maybe another symbols and digits, maybe also after the password, also after the base word. And we call this transformation suffix. Another transformation people tend to do and need to do is the capitalization. So they choose one or maybe more letters to capitalize this letter. And another transformation people tend to do is the lit transformation. Lit transformation is replacing a letter by a symbol or digit, which looks like this letter. For example, we replace the A by the @ sign, which look similar to each other. Okay, so this is the 5 transformation we actually notice that people tend to do. And what we're going to do is we are going to go over a huge corpus of leaked password from the internet. We can freely download this from the internet. And then we learn all the common values of each transformation. So after the learning phase, we actually have 5 lists. And we have all the prefixes people tend to do, all the base word people tend to choose, all the suffixes, they tend to choose the capitalization pattern they tend to do, and all the lead transformation they tend to do. Then after we have these 5 lists, we actually go over these lists and we calculate the probability of each unique item in this list. And then we sort these lists in decreasing order from the highest to the least. So this was the learning phase. Now we're moving on to the estimation phase. So in the estimation phase, we first of all, let's define what is a password in our system. So a password in our system is actually a combination of a prefix, base word, suffix, capitalization, and lead. Now this is a password in our model. Now, what is the probability of this password? So the probability of this password is actually the multiplication of the probabilities of its part. So if the probability of the prefix is Q1 and the probability of the base word is Q2 and of the suffix is Q3 and the capitalization Q4 and so on, the probability of the full password is going to be the multiplication of these 5 probabilities. Okay, now that we understand what is the probability of a password in our model, what we wanted to have is we wanted to have a sorted list of all the possible passwords in this model, of course sorted in decreasing order from the highest to the least, and this would have had the optimal order of password for the crack to try. Now, given a password, how does it help us? Given a password, if we find its position in this list, we actually find the number of attempts a cracker needs to do until he finds this password. So our goal, by the way, we denote this position by the notation rank. So our goal is to find, given a password, we would like to find its rank in this list of all the passwords sorted from the highest to the least. And then, generally speaking, how does it help us? If we receive a password that has a high rank, it means that this is a strong password. Why? Because the cracker will not reach this password in a feasible time. However, if the rank is low, so this is a weak password. Why? Because the cracker will reach this password in a feasible time. So having this list is actually very nice, but the problem is that we cannot generate this list from 2 reasons. First of all, we cannot generate it in advance and then store it because of space consuming. And we cannot also generate it on the fly for any password because this will be time consuming and this is a prohibit. So what we did in our algorithm is we developed a new algorithm that calls ESRank. This is an efficient algorithm, and what this algorithm can do, it can given the probability of a password, it can approximate its rank in this list within the factor of 2. However, without generating this list, therefore it works in fractions of second. So how does it work? Given that we have our password, what we're going to do is we're going to find its transformation, and then we're going to find the probability of each transformation. Then we're going to multiply all the probabilities of all its parts to have the probability of the password. And then given this probability, what we do, we just apply the algorithm that we've developed that calls ESRank. And given this probability, it just returns back the rank of the password, which has this probability in the huge list, although we are not generated. And this happens actually very, very fast. This algorithm is very, very fast. As we can see, the average estimation time per password is very, very low. If we train our system on 33 million passwords, it takes only 0.024, which is very, very fast. And even if we train our model on 900 million passwords, it will be very, very fast. The average will be 0.033. Okay, so far we've seen how to estimate a password that all its transformations exist in the list. But what happens if we receive a password such that one of the transformations does not exist in the list? Let's assume this transformation and this suffix, and let's assume that this suffix does not exist in the list. So in that case, what we do is we are looking at the lowest probability in the corresponding list, which is the suffix, and then we take the lowest and we multiply it by some factor alpha, and this is going to be the probability probability of the unknown suffix. And then we, as before, we just multiply all these 5 values and we receive the probability and we apply the algorithm as before. And this is we call the unleaked smoothing mode. Okay, so now let's compare our algorithm with other methods. So there exists some other method who try to model the behavior of crackers, and we're going to compare ourselves to these 5 methods, which is the Markov model, the PCFG, the Hashcat, the John the Ripper, and the neural network base of Melicher. And as we can see, there are 2 graphs. On the left, we compare ourselves to the Hashcat, PCFG, Markov, and John the Ripper, and on the right, we compare ourselves to the neural network base of Melicher. And these 2 graphs show the accuracy of the model. So the highest is the line. It means that the model is more accurate. And we are the black line, also on the left and on the right. So as you can see, our model is actually more accurate than the models that we compare to. The dashed line, by the way, are the point in which the smoothing mode is inserted, and we chose alpha to be 10 to the power of -3. We also compare the training time of our method with other methods. So the PCFG and the model, when they train on 41 million passwords, so it takes for them days, while for our algorithm, it takes only 12 minutes, which is, of course, much, much faster. And also on a bigger amount of password, when the neural network, they train themselves on 130 million password, it takes days. And for our system, it takes only 35 minutes. Again, very, very fast. Another 2 advantages of our algorithm is that first, it can be personalized. So as I ask you, and most of the people actually tend to use their personal information in their password, again, because it will be easier for them to remember this password. So, and by personal information, I mean name, first name, last name, children name, ID, birthday, and so on. And so this is very common behavior of people. So our algorithm, the PES1, can actually accurate estimate the cracker, how many attempts he's going to do, given that he knows the personal information of the user. So how we're going to do it? It's very easy. So assume that we know the personal information. All what we do is going to the corresponding list, and we just push this information up to the top of the list. So if, for example, we know the personal information Adam, so all what we need to do is just to increase the probability, which means to push it to the top of the list. And this modification takes only fractions of seconds, and of course, without the need to retrain the model, therefore it's very, very useful. And the second advantage of our algorithm is that it can be explainable. Okay, it can explain why we received this rank, and it can give some insight of how to improve your password. And this is, of course, in contrast to some superior method and especially those who based on the neural network, which inherently cannot explain their results. And okay, so let me just conclude. We proposed a novel password strength estimator called PES-rank, and this model accurately models the behavior of a powerful cracker, and this is practical for online use, and the training time of this model is much shorter than the exist method, and it can be personalized without being retraining again, and it can be explainable. And this paper was accepted to the Zurich 2021 conference, and we are going to present it in October in Germany. So thank you very much for your attention, and I would love to take your questions. Yes.
I think I have a question that pretty much everybody has.
Yeah.
Where can I access it?
Okay, so now, so this model, yeah, so actually this model, as you can see, this is an algorithm, but of course we also showed it that we implement this algorithm, and we actually use this algorithm. We integrated this system in a course at Tel Aviv University, a course that Professor Avishai Wool teach. And we integrated it twice in the registration page of this course. We integrated twice, this year and last year. And actually people tried it. I mean, the students, when they register, they try this model, and we receive very good feedback, and they actually improve their password, make it stronger. And so we actually, we implement it and we use it, and we, yeah. You personally. So you will be able to use it when we will come out with this product, like in the future. Yeah.
Do you have any estimation where something like this happens?
So we're actually working on this. So yeah.
Thank you.
Okay. Thank you very much.